All right, let's get into this. We're looking at what seems like a really simple problem, but it's actually a massive engineering challenge.
It really is.
How do you take a basic command, I mean, just a simple on-off switch, and send it over a huge distance, like across a city,
Yeah.
instantly, and, without any errors?
And copper wire just won't cut it. It picks up noise. It has limits.
Exactly. So our mission for this deep dive is to really understand the tech that solves this, but with light.
Right. And what's so fascinating here is the core idea. The device we're looking at, this Thor F-16CC kit, it's basically a perfect electrical translator.
A translator, I like that.
It takes these messy electrical signals and turns them into a clean flash of light. And the key thing is it can handle 16 of these signals all at once, completely independently.
Okay, so 16 channels. And they can carry two pretty different kinds of information, which I think is a really important point for you to get. First, you've got contact closure. Just think of it as the most basic thing possible. A switch is either closed, which is ONN, or it's open, which is O off F.
A physical connection.
Right. But it also handles something called TTL signals. Now, if contact closure is a simple light switch, what's TTL?
TTL is more like a simple computer instruction. It stands for transistor logic, and it's how we send actual digital data.
Like a pulse?
Exactly. A quick pulse that might mean open this gate right now. This kit specifically handles 5VPP TTL pulses, which just means it's reading a very clear, standardized digital high or low signal. So it perfectly copies a digital command, not just, the status of a switch.
So if the whole mechanism is just this kind of reliable optical mirror, what does this setup actually look like? Are you limited to just a one-to-one connection?
Oh, that's a great question. And no, absolutely not.
Okay.
You can do a simple point-to-point connection, which is the most common setup. But the sources also make a big deal about daisy chain configurations.
Which means?
It means you can string multiple receivers along the same fiber line. It's critical for complex systems, like a security network that has to trigger 10 different alarms in a row across a huge facility.
And the whole reason we're using fiber here is all about getting over long distances.
Distance is the big one, yeah. But I'd almost argue that the isolation is even more important. The base unit can do 20 kilometers over single-mode fiber. That's just an incredible range for a switch command.
20 kilometers.
But the real magic is what fiber gets rid of. You have zero EMI or RFI, so no interference from radio towers or power lines. And you completely eliminate the nightmare of ground loops.
Okay, let's stop on ground loops for a second, because that's a huge aha moment for anyone who's ever run a long cable.
It really is.
A ground loop is basically when electricity finds multiple paths to ground, and that creates these unwanted currents that just scramble your signal.
Precisely. But with fiber, you're using light, not electricity. You physically cut the electrical path.
It's a clean break.
It's total electrical isolation. And that is why this technology is used in systems where failure is just not an option.
Which brings up applications. And who really needs 16 channels of perfectly clean long-distance switching?
You'd be surprised. You have to look at critical infrastructure. We're talking access control systems, building automation, fire and alarm systems for instant triggers.
Things that have to work.
They have to work. And definitely things like traffic signal control equipment. Fiber is really the only way you can guarantee that a traffic light 20 kilometers away changes the instant you tell it to without any delay or interference.
So if you're relying on this for, city traffic, the reliability has to be rock solid. The sources mentioned some pretty impressive numbers here.
They did.
It's a plug-and-play design, which is great. But the operating temperature range is, wow, minus 20 degrees C all the way up to 75 degrees C.
And that's essential. These things live in hot roadside cabinets or cold utility closets. But the real number is the MTBF.
Mean time between failures.
Right. It's rated for over 100,000 hours. So for you listening, that means this thing is designed to run for more than 11 years continuously before a failure is even statistically likely.
11 years. In a traffic system, that's the difference between a smooth commute and total gridlock.
It's everything.
So wrapping this up, what this deep dive really shows is how modern engineering can take the most basic state on or off and turn it into a flawless beam of light.
You get fast, totally isolated, and incredibly reliable remote control over huge distances. It's sophisticated engineering for the simplest switch.
So for your final thought, think about this. The next time you see a security gate swing open or a traffic light change, just realize how much that relies on these tiny, robust optical links. They're like an invisible nervous system for our infrastructure, constantly translating a physical action into data and then right back again.